Alright, in our last section of Unit 8, Lesson 8.7, we're going to discuss a couple of topics, and these are a little bit more advanced topics, but what I'm going to do is I'm going to try to get to just the basics of each. So we're going to do a little bit of description here first on systems of linear equations, and then I'll show you a very simple example or two of graph of linear inequalities. Alright, now let's go back to the idea of what a linear equation in two variables is. A linear equation in two variables that has an x and a y, right? It has infinitely many solutions. For example, if I write down y equals x plus 3, a solution to this equation would be if x is 0, y is 3. Or if x is 1, y is 4. Or if x is 2, y is 5. I can make as many as I want by plugging in numbers for x and determining the y by adding 3. We write those as ordered pairs x, y. So this is going to have an infinite number of ordered pairs x, y that are going to make that true. Any linear equation in two variables is going to have infinitely many solutions. So since we cannot list them all, what we have been doing is we've been representing them graphically. We've been plotting these ordered pairs on the Cartesian plane, on the xy axis, and we've been getting lines. That's why they're called linear equations. If you graph all of those ordered pairs as points, all those points are collinear. They all line up and they form a line. So to represent an infinite number of solutions, we think of a linear equation in two variables as a line. That's the equation and the graph is the line. Now, a system means more than one. If we have two linear equations in two variables, what we're going to do is we're going to check to see if they have a common solution. If we have two equations, here's one right here, here's another one right here. This has infinitely many solutions, this has infinitely many solutions. Do they have any solutions in common? Well, that's where we're going to get a couple of definitions here, and then I'm going to try to explain that best I can. Now remember, if we graph that, this is a line. And if we graph that, this is a line. So one of three things is going to happen if we graph two lines on the same set of axes. They're either going to be parallel, they're going to cross at a single point, they're either going to be parallel, they're going to cross at a single point, or it turns out it's the same exact line and we're going to have every point on the line in common. Every ordered pair to one would be an ordered pair to the other. So now, what is a system of linear equations? Well, the book calls it a linear system. It's two or more linear equations have the same variables. Must have the same variables. Now, we'll be looking at what we call 2x2 systems. Those 2x2 systems, that's two equations with two variables. The same two variables. Now, a solution to a linear equation in two variables is an ordered pair. That's a solution of each equation. It has to satisfy both. It can't just make one of them. It's got to make both of them true. Okay, we're going to determine if the ordered pair -2, -3 is a solution to the system. That means it's got to make both of them true. It's got to satisfy both. Remember, this is your x and this is your y. Substitute in for the x and y variables in both. Let's try the top one. If I plug -3 in for y and -2 in for x, I get -3 equals 3 times -2 plus 3. That's -3 equals -6 plus 3. That's -3 equals -3. So it makes the first one true. Let's try the second. Now -2 in for x, that's going to be the opposite of x, and -3 in for y. So I get -3 equals -2 in for x. The opposite of -2 is 2 minus 5. Well, that's the same thing as 2 plus -5. And if you add a negative or a positive 2 and a -5, that's a 3 here, you do get a -3. So that one is a solution. Your answer to this one would be yes, because it satisfies both equations. If it had made either one false, then we would have said no, it's not a solution. Next, what we'll do is we're going to go ahead and we're going to use the graph of a system of linear equations. See the two lines graphed here in this example, to identify the actual solution to this system that it represents. Now remember, I said when you are graphing two lines, a system, one of three things can happen. They can be parallel and not cross. They can intersect at a single point. That's this example right here. Or they can turn out to be the same line and have infinitely many points in common. In this case, we have one ordered pair, and you can see it. It's right here. It's where the lines cross. That's the ordered pair 2, 1. Remember, start at the origin, go right, left first, then up, down. I'm 2 to the right, up 1, 2, 1. Okay, and that's the solution. That's all there was to that one. There's a little bit more if you have to graph it, and that's what I'm going to do with this example. I'm going to do a very basic one by graphing. Where the graph's not given, we do the graph itself. Now, even though we haven't done a line like this in a while, this particular, where it doesn't have the y, just the x, this is the graph of the equation of a vertical line, x equals 2. So, let me set my scale. X equals 2 would be a vertical line right through the point 2, 0 on the x-axis. Remember, this is your x-axis, this is your y-axis. This is your x-axis, this is your y-axis. So now I'm going to graph the other line, which fortunately for me is in slope-intercept form. Even though there's no number written there, it's understood that my slope is 1 and that my y-intercept is 0, negative 1. 0, negative 1 is right there. My slope is 1, which means I'm going to go up 1 to the right 1. Because remember, think of it as 1 over 1, rise over run. And if I draw this line, and I'll do the best I can here, I can see that it crosses right here. These two lines cross right here at the point 2 to the right, 1 up, at the point 2, 1. You say, well, is it always 2, 1? No, that was a coincidence. It's not always 2, 1. Don't put 2, 1 down every time you hit a system of equations. Now, once we've got a good feel for this, we're going to go on to another topic here about a linear inequality in two variables. Now, linear equations in two variables, we've had those. A linear inequality, there's a little change. A linear inequality in two variables is the result of replacing the equal sign in a linear equation like this with either a greater than, a less than, a greater than or equal to, or a less than or equal to sign. So we're changing it. We're getting rid of the equal sign. We're putting one of those 4 symbols in there in its place. Now, a solution to a system in two variables is an ordered pair xy, that when we substitute them in for the variables, in the inequality, we get a true statement. So it satisfies the inequality. And we'll do an example of that next. Okay, here we are. Example, tell whether the ordered pair is a solution to the inequality here. And you can tell it's an inequality. It's got a greater than sign. 3x plus 4y is greater than 10. Not equal to 10, greater than 10. So what we're going to do is we're just going to substitute right in. This is our x and this is our y. This is going to go right in there. This is going to go right in there. I have 3 times negative 3 plus 4 times 4 greater than 10. 3 times negative 3 is negative 9. 4 times 4 is 16. Negative 9 and 16 is 7. Oh, 7 is not greater than 10. So, nope, not this one. Let's try this guy over here. We're going to plug this guy in for the x and this guy in for the y back into here. So it's 3 times 5 plus 4 times negative 1, that's the y, is greater than 10. This is 15 plus negative 4 is greater than 10. A positive 15 and a negative 4 is 11. And 11 is greater than 10, so this one is a solution. It has an infinite number of solutions. Again, since we can't list all possible solutions to an inequality in two variables, we do the next best thing, we draw a picture, we graph the solutions. And that's what I'm going to do. I'm going to finish this lesson with one example of a graph of a linear inequality in two variables here. Now, you'll see this time I have a less than or equal to symbol for my inequality sign. But to graph this, I need the boundary line. The boundary line comes from when you change this back into an equal sign. This has slope 1. It has y-intercept 0, negative 1. So I'm going to grab 0, negative 1. Slope is 1, which is like 1 over 1. So rise over run, just like we did in a previous lesson in this chapter. Now, what I'm going to do next is I'm going to draw the boundary line. So you say, well, just draw the line that goes between them. When we did the inequalities in one variable a while back, we had graphs on the number line. We had open circles and filled in circles. Filled in if it had the equal to, like this one. Open circles if it didn't. So since we can't have filled in lines and open lines in the same manner, we'll have solid lines or dotted lines. Solid lines for when it has the equal to, dotted for when it does not have the equal to. This one's going to be a solid line. I'm going to draw right here, best that I can, and you can see that my line breaks up the Cartesian plane. Now remember, this is the x-axis, this is the y-axis, into two half planes. This half plane up here, this half plane down here. One of the half planes has the solution, one of them doesn't. That's why this is a boundary line. It separates the answers from those that we want to those that don't work, that we don't want. So all we have to do is determine, is it up here, is it down here, and represent that. The easiest way I have found to do that is to take a point that's not on the boundary line, like I like 0, 0. 0, 0 is not on the boundary line, and the reason I like 0, 0 is because it's easy to substitute in and evaluate, because anytime you plug in 0, most of the time it just falls apart. I'm plugging this in for x, I'm plugging this in for y, just like we did up here to see if it's a solution. 0, 0, which is in this half plane, I'm going to see if it's a solution or not. So I'm going to plug them in to the inequality. I get 0 is less than or equal to 0 minus 1. I get 0 is less than or equal to negative 1, which is false. So since 0, 0 in this half plane makes it false, all these will make it false. Every single point in here will make it false, which means every single point in here will make it true. To represent that, we shade it in, and I normally just draw a bunch of parallel looking lines like this to represent that I'm shading this side in. And that's the graphic representation of the solution of an inequality in two variables. See, it's a lot simpler just to substitute the ordered pair in to see if a particular point is a solution or not. A little bit more difficult to find a graphic representation of all the solutions. But you can get good at it. It just takes practice, practice, practice.